Okay, this video is to clarify some aspects of Bode plots. This will help you in following contents of the course that we will be doing this semester. So I begin by considering a first order circuit. So let's go back to the simple prototypical first order circuit that we had, wherein I have an input voltage given by Vp angle 0, and say I have a resistor R and a capacitor C, and I am interested in the voltage across the capacitor. Let me call that Vc with its polarity marked thus. Let me define omega 0 to be 1 by Rc, and you will find that subsequently we will refer to omega 0 as the corner frequency, it will become clear as to why we refer to omega 0 as the corner frequency. I can write out an expression for say the voltage across the resistor and the voltage across the capacitor as if I am interested in the voltage across the resistor, that is Vr, that would be Vp angle 0 divided by R plus 1 by j omega c. That would be the current flowing in the circuit multiplied by the resistance R, and this can be simplified to Vp angle 0 divided by 1 plus j omega c R the whole into j omega c R, which can further be simplified as Vp omega c R divided by square root of 1 plus omega squared c squared R squared. The numerator has an angle of pi by 2 corresponding to the j, and the denominator has an angle of tan inverse omega c R, which effectively gives you Vp into omega by omega 0 divided by square root of 1 plus omega by omega 0 the whole squared, and an angle which is given by pi 2 minus tan inverse of omega by omega 0. So far we have not done anything fancy. This is just algebraic manipulation. This quantity is the magnitude, and that quantity is the phase. And so plot, for example, a function magnitude and phase as functions of omega. So plot that here. So if I look at the magnitude, which let me call the magnitude itself is just the magnitude of VR divided by Vs, right? At low frequency, you will see that this particular function, what happens to this particular function at low frequencies? So at low frequencies, this particular function tends to 0, right? And at high frequencies, you can neglect 1 with respect to omega by omega 0 squared, and hence at high frequencies this function tends to 1. So the itself will look something like this. If I plot this as 1, then at low frequencies I'm at 0, and then at higher frequencies I go up, and asymptotic I reach 1, right? And what happens at omega equal omega 0? At omega equal to omega 0, I hit the value of, at omega equal to omega 0, I hit a value of by root 2. Alright, and similarly I can put the phase of VR divided by Vs, and the phase again corresponding to this particular drawn above. What's the phase angle? What is the phase angle? Omega being 0 is 90 degrees, right? So the phase angle is pi by 2 at, so that is pi by 2. Then at omega equal to omega 0, what happens? At omega equal to omega 0, you have tan inverse of 1, which is going to be pi by 4. So pi by minus pi by 4. So at omega equal to omega 0, I have a phase of pi by 4, right? And as omega tends to infinity, this phase angle will tend to 0. So phase itself goes something like that. Okay. All right. So this is an exact plot of the phase and the magnitude as we sweep the frequency omega. So you can notice why we refer to omega 0 as the corner frequency, because you sense that there is a change in the nature of this function around this corner frequency. Alright? Okay. Many times we are not really interested in the exact shape of the function corresponding to the magnitude and the phase. We are more interested in some kind of approximate trend. So let's go back and see if we can approximate this particular function. Okay, so I'm going to start. Let me start with this. Okay. So I had a VR, right, as being equal to this guy, correct? Which means that if I were to define a trans function h of omega, which let me define as VR divided by Vs, both VR and Vs are the phase quantities, then this quantity is nothing but j omega by omega 0 divided by 1 plus j omega by omega 0. Alright, so let's consider this particular function, and let's look at the situation for small and large omegas. Alright, so the idea here is that we want to be able to write out an expression or plot the magnitude of h of omega without really having to calculate the exact magnitude of h of omega from this complex function. Okay. So we plot the magnitude in terms of what's known as the logarithmic scale, specific, we plot the quantity 20 log 2 base 10 of modulus of h of omega, and the quantity is referred to as number in decibels, abbreviated as dB. Why do you have 20 here? Well, the 20 comes from the fact that you have a voltage in this. Now, the h of omega here is a ratio of voltages. Power in itself goes as V square, and so when you have the 20, you're effectively measuring ratio of powers. So if I were to the magnitude of h omega in decibels, I can take two limits. One is the limit of very small omega. So the limit of very small omega, so omega less than omega 0, will do h of omega tends to j omega by omega 0, because omega by omega 0 is less than 1, and hence I can drop this quantity with respect to 1, right? So the magnitude of h of omega goes as omega by omega 0, which means that 20 log 2 base 10 of magnitude of h of omega goes 20 log 2 base 10 of omega by omega 0. What happens to the situation where omega is much greater than omega 0? So in the situation where omega is much greater than omega 0, this implies that h of omega tends to j omega by omega 0 divided by j omega by omega 0, because I can select 1 with respect to this t of j omega by omega 0, which equal to 1, implies 20 log 2 base 10 of modulus of h of omega effectively becomes equal to 0. By omega less than omega 0, what we effectively mean is omega less than omega 0 by 10, and by omega greater than omega 0 effectively mean omega greater than 10 omega. That's the engineering approximation for less than greater than. So one go ahead and plot this function. So let me say that this is 0 dB, let me say it as 20 dB, and that is minus 20 dB, and let me say that my omega 0 is here, my 0.1 omega 0 is there, and 10 omega 0 is there. Then first let's take the situation of omega greater than omega 0. The magnitude in decibels is going to be 0 dB, so effectively I am here, right? The trick in making Bode plots is that you use approximation for omega greater than 10 omega 0, but extend that approximation all the way until the corner frequency, which means that you extend it all the way there. Similarly, let's take the situation of omega less than omega 0 by, which is less than 0.1 omega 0, right? In that case, you have to plot this quantity 20 log omega by omega 0, right? What's the value of this quantity when omega equal to 0.1 omega 0? 0.1 omega 0 divided by omega 0 is effectively log of 0.1, which is minus 1. So this quantity then is minus 20 dB. So you know that this quantity minus 20 dB at 0.1 omega 0. And what about this quantity at say 0.01 omega 0? That would be minus 40 dB. So minus 40 dB would be where here. And so we can again go ahead and draw a line connecting these two, and following the idea that we used for the greater than omega 0 case, extend this all the way onto the corner frequency. Correct? So this then is a part of 20 log 2 base 10 modulus of . Okay, so this is called as the Bode magnitude plot, and if one were to actually ask the question as to how this function would actually look and not the approximate case, then the actual plot will look something like this. For less than 0.1 omega 0, you're pretty much there. Then here you begin to deviate a little bit, and then you deviate there, and then also again for greater than 10 omega 0, you're going to be pretty close to what the asymptotic limit would be, right? And at omega equal to omega 0, you can find out what this value is going to be, and you can show that this is actually 3 dB. So omega equal to omega 0 is also called as the 3 dB point, or rather, yeah, so it's minus 3 dB in this case, right? And you can also make a comment that in this region where the system attenuates the input voltage, you have a slope which corresponds to 20 dB per decade. This is an important number to remember, because what we are studying here is a first order system, and for a first order system usually you have a roll off, or in this case an attenuation of 20 dB per decade. In the case of second order systems, this 20 dB per decade becomes 40 for third order, 60, and so forth. All right. So this is the situation for VR. One can also look now at the situation for VC. So what is the expression for VC? What is the expression for VC? Let's go back and have our circuit again. So the expression for V is just a voltage divider. So you're going to get VC equal to Vp divided by 1 by j omega c, right, divided by 1 by j omega c plus r. Is would be effectively Vp divided by 1 plus j omega cr, which means the ratio of C by VR, which is Vc by s, which is what we want. The ratio of Vc by Vs is going to be 1 by 1 plus j omega by omega 0. Right? And if I want to plot the Bode magnitude plot for this, again I need to consider two situations. I can now do this by inspection, omega less than omega 0, in which case the Bode magnitude plot effectively give you what would it be? If omega is less than omega 0, you drop this with respect to 1, so this would be 3b, and for omega greater than omega 0, you can drop 1 with respect to this, and so this would minus 20 log 2 base 10 of omega by omega 0, right? And so you can go ahead and plot this function. I say equal to omega 0, 1 omega 0 and 10 omega 0. Then for omega greater than 0, which means omega greater than 10 omega 0, we are exactly at 0. Right? No, wrong there. For omega less than omega 0, I am exactly at 0 dB. So here I am at that, and then I have to extend it because the approximation until the corner frequency. So this is 0 dB, that is 0 dB, say that's 20 dB, and say here we have minus 20 dB. At 10 omega 0, I'm going to be at minus 20 dB, right? When this is 10 omega by omega 0, so log 10, which would be 1, so minus 20 dB. And at 100 omega 0, I will be at minus 40 dB. So I go ahead and join the by a straight line and extend this line all the way to frequency, right? So yeah, that should be a straight line. Okay. That doesn't look like a straight line, but you get the idea. Okay, so then is your Bode magnitude plot, and you see this function actually is what kind of is this? This is a low pass filter. Alright, and you have a roll off of given by 20 minus 20 dB per decade. Okay. So now we can, with this general idea, you can look at any generic function. So let's a generic function, and with that be done. Let me take a generic function of this form. Let me assume that my this is an example of some kind of if my h of omega were equal to 1 plus j omega by omega 1 divided by 1 plus j omega by omega 2 and 1 plus j omega by omega 3, and let me say that omega 1 less than omega 2 less than omega 3, right? And further, let me say that omega 1 is less than 0.1 omega 2, which effectively means that this is less than omega 2. And let me say that omega 3 is greater than 10 times omega 2, which means this is greater than omega 3, right? So for this kind of transformation, again you can just take the three independent quantities, plot, and then add their logarithms, right? Because you have here things which go as a product, and there's a division relation and there's a product relation. When you take a log, that becomes either a subtraction or an addition, right? So this is fairly stable. Right, and let me start with omega 1, right, and let me say 10 over 1, right, and let me put omega 2 here, and let me mark 10 over 2, right, and then let me mark omega 3 here, right, and I will have 10 omega 3, right. And just to be clear, let me just circle the omega 1, omega 2 and 3. Further, if I have omega 2 there, then I'm going to have 0.1 omega 2 here. If I have omega 3 there, I will have 0.13, right, and that's good enough for me. So let's plot this term, plot that in blue. Let me call this T1, 1 plus j omega by omega 1, and in this case, let me just make this as 0 for ease of plotting. Let me call that as 0 dB, let me call this minus 20 and that plus 20, correct? So how does this function look? 1 plus right. So this function is going to be, I'm going to draw this in blue, it will be until there, right? Until omega 1, and then from omega 1 and it should be there, so this function goes like that, right? So that's T1, it will go further. Okay, let's take T2, which is omega 2. Let me draw that in red. So how will that be? Okay. So that's also going to add 0 dB. Therefore, be at 0 dB all the way until omega 2, right? And then it will drop off at 20 dB per decade. So you will come here and you can extend that line like so. That is T2. Okay, and let me say in green, let me plot T3. How will that look? It will look similar to the T2 case, just with a shift to omega. So I'm going to have line all the way until omega 3, right? And then subsequently going to roll off at 20 dB per decade and continue down. Okay, so the magnitude plot for h of omega itself is just going to be sum of the blue line, the green line, the red line, right? It's fairly straightforward, and I'm going to plot that in magenta and with a thick color, right? So all the way from here to here, you're just going to add 0 plus 0, so there's no change, right? Here you're going to add this line plus a 0, so you're going to basically follow this line all the way until here, correct? Subsequently, in fact, you will follow this all the way until omega, right? This will, you will follow this all the way until omega 2. After omega 2, this 20 dB per decade line and this minus 20 per decade line will compensate, and that will effectively make you go flat all the way till omega 3, right? And then subsequently you only have the minus 20 dB per decade line corresponding to omega 3, and you will down like that, something like that, right? So this would be the Bode magnitude plot for H omega. So the idea is that you should be able to so the final goal, which I hope conveyed in this short lecture, is that you should be able to plot the magnitude plot by inspection. You should not go and try and actually calculate modulus of h of omega, right? When h of omega is written in this form of 1 plus a omega by omega x, or of the form omega by omega x, then just by considering the various terms that go into this function,